Hey fellow nerds. Today we're going to discuss the low and mid frequency analysis of common emitter amplifiers. We will be discussing the common emitter amplifier, its small signal hybrid pi model, voltage gain, emitter degeneration, RC coupling, frequency response, input impedance, and output impedance. First, let me explain to you why this is called the low and mid frequency analysis. For that, we have to go inside the transistor. You can see that at the base emitter junction, there are electrons on this side, holes on this side. In between, we have the depletion region where there are no charges. So basically, there is a separation of opposite charges. At the collector base junction also, you can see the same thing. We have holes here, we have electrons here. In between, there is depletion region where there are no charges. Basically, at the base emitter and the collector base junctions, opposite charges are separated by the depletion layers. And when opposite charges are separated by a distance, it gives rise to a capacitance. Since this is happening at a PN junction, we call this a junction capacitance. Now, we know capacitive reactance is defined as 1 by omega C. Omega is the frequency of the signal, C is the capacitance of the capacitor. Capacitive reactance is inversely proportional to omega. Here, if we assume that our signal is of low or mid frequency, we can assume that omega is a small value and therefore xc is a large value. How does it matter in the performance of our circuit? To understand that, let me take a circuit with two resistors in parallel. I have a 1 kilo ohm resistor and a 10 ohm resistor. One of them is really larger than the other one. Let's calculate the equivalent resistance of the circuit. It is 1000 times 10 divided by 1000 plus 10. This comes out to be around 9.9 ohm. This is approximately equal to 10 ohm itself. So in this circuit, even if you remove the 1 kilo ohm resistor, it is not going to affect the performance of the circuit in any way. Now assume that instead of 1 kilo ohm, you have a 10 kilo ohm. Then the equivalent resistance will be even closer to 10 ohm and you will be able to remove the larger resistance without affecting the circuit. Let's try this one more way. Instead of the equivalent resistance, I want to calculate the current that will flow through the 10 ohm and 1 kilo ohm. Both resistors have the same potential across them, 10 volt. So current through 1 kilo ohm will be 10 divided by 1000, that is 0.01 ampere. Current through 10 ohm will be 10 divided by 10, that is 1 ampere. Here the current through the 10 ohm resistor is 100 times more than the other one. Very little current is flowing through the 1 kilo ohm resistor, so you can easily remove it. The larger the resistance, the more irrelevant it becomes in the circuit. Now imagine instead of the resistor, we have a capacitor there. It has a capacitance C. But in the first video of this series, we have learned that the property of a capacitor that is equivalent to the resistance of a resistor is not the capacitance, it is the capacitive reactance. Now, if the capacitive reactance is too large, you can ignore the capacitor just like you ignored the larger resistance in the previous case. It will not affect our circuit at all. Here's how we'll be applying this idea in our analysis of the common emitter amplifier. If we take that our signals are of low and mid frequencies, then the capacitive reactances can be considered too large when compared to the other resistances we'll be adding in the circuit. And therefore, they will have negligible effect in the circuit and we'll be completely ignoring them. So basically, when we say low and mid frequency analysis, we mean that we are not going to acknowledge the presence of any junction capacitance. Now, let's take a basic common emitter amplifier. I have given the VCC supply in the collector. I have the collector resistor, which will also act as the load in this case. I have given V0 for biasing. Input is given at the base. Output is taken from the collector. Let's take some values for example. I have removed the input for now. We will only calculate the bias conditions. V0 is 0.7 volt. RC is 1 kilo ohm. VCC is 2.5 volt. and IC naught is 1 milliampere. Why have I called the collector current IC naught? Because once we apply the signal, the IC we get is going to be IC naught due to the biasing plus GMV input due to the input. Right now we don't have the input, we have only done the biasing. So the collector current we get will be IC naught. Here V naught is directly connected between the base and emitter. So the base emitter voltage is going to be V naught, which is 0.7 volt. Now I want the value of voltage across the collector resistor. For that, I know the current that is flowing through it, IC naught. I also know the resistance RC. IC naught is 1 milliampere, RC is 1 kilo ohm. So the voltage across it is going to be IC naught RC, which is 1 milliampere multiplied by 1 kilo ohm, which is simply 1 volt. The next thing I want to find out is the value of the output voltage. For that, I am going to use KVL because I have given VCC over here. Out of that, IC naught RC will be dropped across the resistor RC and I will get the rest at the output. So using KVL, V output will be VCC minus IC naught RC. I have all the values. VCC is 2.5 volt. IC naught RC, we already found it is 1 volt. So the output voltage is going to be 1.5 volt. Now let's keep all these values aside. I am going to apply my input signal, which is sinusoidal. I am going to call the collector current IC now. IC will be, as you know, IC naught plus the new collector current due to the input GMV input. Assuming the input is a sinusoidal signal, let us take V input to be Vm sine omega t. Its frequency is omega, its maximum value is Vm. Then, if I want the collector current, I know it is IC naught plus GMV input. I already know the value of IC naught, it is 1 milliampere. In that case, the potential across RC, VRC is going to be IC naught RC plus GMRC V input. Basically, total IC multiplied by a resistance RC according to Ohm's law. Now, I already know the value of IC naught RC. So, after applying the signal, potential across RC will be 1 volt plus GMRC V input. Obviously, 1 volt is a DC value. GM is a constant, RC is a constant, V input is sinusoidally varying. So GM-RC V input is an amplified version of the input voltage. It is sinusoidal. Basically, we can say that voltage across RC has a DC component and an amplified version of the input voltage. Finally, I want to find out the output voltage. Just like we did earlier, I have applied VCC. Out of that, IC-RC will be dropped across RC. The rest I will get as the V output. So V output will be VCC minus IC-RC. But IC is IC naught plus GMV input. So we can write VCC minus IC naught plus GMV input multiplied by RC. Or we can write VCC minus IC naught RC minus GM-RCV input. I know the value of VCC minus IC naught RC. We have already found it over here. It is our previous output when the input was not connected. It is 1.5 volt. So the current V output is going to be 1.5 minus GM-RCV input. Again, this is a DC value and we have an amplified version of input. This is not just an amplified version of input, there is a negative. So this is an inverted and amplified version of the input. Now, for better understanding, let us visualize these using graphs. Our input voltage is Vm sine omega t. Assume this is Vm sine omega t. Now, I want to plot VRC, voltage across RC. It has V input multiplied by GMRC, that is an amplified version of input voltage, and a DC value of 1 added to it. So first I will take an amplified version of the input voltage. This is the voltage across this is the voltage across the collector resistor. Let us now plot the output voltage. Here I have V input that is multiplied with minus GMRC. So it is an amplified version of input which is also inverted. Along with that, I also have to add a DC value of 1.5. First, let me take an inverted and amplified version of our input. Now I will add 1.5 volt to it. This is how our output will look like. Let us now see how to make the small signal model of a common emitter amplifier. For that, I have taken the circuit of a basic common emitter amplifier over here. To make its small signal model, first let me take the small signal hybrid pi model of a transistor. We know in the small signal model, V naught will be shorted. V input is connected at the base, so let us show it. VCC can be considered as a cell of potential VCC that goes to the ground. VCC will also be shorted in the small signal model, so RC will be connected to the ground. Basically, RC will be between the collector and the ground. Let us show it in the small signal model. Finally, the output is taken at the collector. In the actual circuit, emitter is connected to the ground. In the small signal model, also, emitter is connected to the ground. In the actual circuit, V input is not connected to the ground, but in the small signal model, it is. Similarly, RC in the actual circuit is not directly connected to the ground, but in the small signal model, it is. What I'm trying to say is the ground that we see in the small signal model is not exactly the physical ground that we see over here in the original circuit. You can see that this point that we have taken as a ground in the small signal model is actually this point. It is obviously not the ground. This point that we have taken as a ground in the small signal model is actually this point, which is obviously not the ground. We took them as grounds when we ignored the effect of DC supplies. So these points are grounds only for our AC small signal input. Because of that, we call it the AC ground. Now, assume that instead of biasing the transistor using a cell over here, I use a voltage divider bias. How will it change our small signal model? Since VCC is a DC supply, it will be grounded in the small signal model. So you can see R1 is connected between the base and the AC ground. R2 is also connected between the base and the AC ground. So in the small signal model, we can show them like this. We can connect both R1 and R2 between the base and ground. There is another way of doing it. Instead of taking R1 and R2, you can take the Thevenin equivalent of them. Then the actual circuit will look like this. I have added the Thevenin equivalent resistance and the Thevenin equivalent voltage. VTH again is DC, so we'll have to short it. RTH, as you can see, is connected between the base and the input voltage. So in the small signal model, we can show it like this. It is connected between the base and the positive terminal of the input, just like how we have in the actual circuit. Now, instead of this, what if I'm using a fixed bias? We will have RB that is connected between the base and VCC. In the small signal model, VCC will be grounded. So RB will be between the base and our AC ground. We can show that in the small signal model like this. Between the base and the AC ground. Now, what if I have self-bias instead of this? In this case, the base resistor will be connected between the base and the collector. So in the small signal model, we can show it like this. Now that we have a solid understanding of creating the small signal model of a CE amplifier, let us move on to its analysis. In case 1, we will ignore the early effect, which basically means we are taking the early voltage to be infinite. I have the circuit of a basic common emitter amplifier. I have also made its small signal model. Now, before we start, one thing I'm going to do is calculate the current that is flowing through RC. You can see that over here, RC has a voltage that is equal to output voltage. Over here, it has ground. So, the current flowing through RC will be V output minus 0 divided by RC. Let us mark it over here. Now you can see that the input voltage is directly connected across R pi. How? Positive terminal of the input is at this point of R pi. Negative terminal through the ground is connected to this point of the R pi. So technically the potential across R pi will be equal to V input. V pi will be equal to V input. Let us write it down. Over here, we have the dependent current source whose value is GM pi. But we just found out V pi is equal to V input. So GM pi will be equal to GM V input. Now let's apply KCL at the collector. This is our collector node. There are two currents flowing. First one is this one. The second one is this one. V output by RC is flowing out of the node. GM pi is also flowing out of the node. That is, GM pi plus V out by RC should be equal to 0. Here, instead of V pi, I have written V in because obviously V pi is equal to V input. This gives us GM input is minus of V output by RC. What we want to find out is our voltage gain. It is the output voltage divided by input voltage. From this, we can write V output by V input is minus GM-RC, which means the voltage gain of this common emitter amplifier is minus GM-RC. GM being the transconductance and RC being our collector resistor. The output voltage will be minus GM-RC times the input voltage. It will be amplified and inverted. Let's take an example and give some values. Assume RC is 1 kilo ohm, VCC is 2.5 volt, IC0 is 1 milliampere. Our gain is minus GM-RC. I want to double our gain. Well, gain depends on GM and RC. So there are two ways in which I can do it. I can double the GM or I can double RC, right? Let's take the first case. To double the gain, I'm going to double RC. Let us see what happens to the bias conditions if we double RC. You can see that we apply VCC, out of which some voltage will be dropped across RC and the rest will be given out as V output. If I only take the bias conditions, the current flowing through RC will be IC0 and the voltage across it will be IC0 RC. V output will be VCC minus IC0 RC. I have all the values. VCC is 2.5 volt. IC0 is 1 milliampere. RC is 1 kilo ohm. So I will get 2.5 minus 1, that is 1.5. But I want to double RC. Instead of 1 kilo ohm, I will take 2 kilo ohm. Then what happens? It will be 2.5 minus 1 milliampere multiplied by 2 kilo ohm. That will be 2.5 minus 2 or 0.5 volt. Now, what is the problem with that? See the circuit again. We have V output here. This is collector. This is emitter. And then it goes to ground. So basically, V output is the voltage that we get between the collector and emitter. V output is equal to VCE in this case. So if V output becomes 0.5 volt, basically VCE is becoming 0.5. If VCE is 0.5 volt, that means VCE is less than VBE, which should be 0.7 volt. A condition we had for a bipolar junction transistor to work as an amplifier is that VCE should be greater than VBE. Now, by doubling RC, our VCE has become lesser than VBE. That means our transistor has gone to saturation. Let's try the other one. I will double GM to double the gain. We know GM is IC naught by VT. VT is thermal voltage, it is constant for a given temperature. So if GM is doubled, IC naught will double. Again, V output can be written as VCC minus IC naught RC. VCC is 2.5 volt. IC naught used to be 1 milliampere. We are doubling it. It will become 2 milliampere. RC is 1 kilo ohm. So we will get 2.5 minus 2 milli multiplied by 1 kilo, which is again 0.5 volt. VCC is 0.5 volt, which means basically VCE is 0.5 volt. Again, our VCE becomes lesser than VBE and our transistor goes to saturation. The conclusion we can make from here is this. Increasing RC or GM does not necessarily increase our gain. Let us see the second case where we have to include the early effect, which means the early voltage is less than infinity or a finite value. I have taken the basic circuit of a common emitter amplifier. I have also drawn its small signal model. We have already learned that in case early effect is included, we have to add R naught between the collector and emitter. Here you can see R naught is connected to the collector. It is also connected to the emitter through the ground. Now you can see that RC and R naught are basically in parallel. So instead of showing them separately, we can model them as one single resistor whose resistance is RC parallel to R naught. This will simplify our circuit, so let us do that. Now, one end of this resistor has potential V output, the other end has 0. So the current through it is going to be V output minus 0 divided by RC parallel to R0. Let us show it over here. Now, again you can see input voltage is directly connected across R pi, which means V pi is going to be equal to V input. Over here, we have GM pi. If V pi is equal to V input, we can write GM pi is equal to GM in. Just like we did earlier, let us apply KCL at the collector. I can see two currents. One is GM pi or GM input that is going out of the node. The other is V output divided by RC parallel to R0, which is also going out of the node. According to Kirchhoff's current law, the sum of these two currents should be equal to 0. So we can write GMV input plus V output by RC parallel to R0 is equal to 0. Or GMV input is negative of V out divided by RC parallel R0. What we have to find out is the voltage gain, which is basically V output divided by V input. From this equation, we can write V output divided by V input. It is minus GM multiplied by RC parallel to R0. So this will be our voltage gain. When we did not have R0, our gain was minus GM RC. With R0, it is minus GM RC parallel to R0. So we can say that technically the voltage gain is minus GM multiplied by equivalent resistance between the collector and AC ground. If I had one more resistor over here, which is, let us say, R1, then I can take the equivalent of RC parallel to R0 and R1. R1 is also parallel to them. The equivalent will become RC parallel to R0 parallel to R1, and my gain will become minus GM multiplied by RC parallel to R0 parallel to R1. Let us take the third case. Here, instead of putting a resistor over here, I have a current source which is giving me my collector current IC. How is this going to change our small signal model? Well, this is how it will look like. At the collector, I have opened the circuit where I had the current source. Why? Because the current source basically is a DC source which I have to remove in the small signal model. Now, when we say remove a voltage, it means the voltage should become 0. If the voltage between these 2 points should become 0, I have to short it. Similarly, when I say the current source has to be removed, it means the current should become 0. If the current between these 2 points should become 0, I have to open it, not short. So, in the small signal model, I have opened it, which basically means we do not have a resistor over here to take the output from. So, I am going to include early effect, so I will have R naught over there. Now, for R naught, potential across it is V output. So, the current through it will be V output divided by R naught. If you want, we could do all the math and find out the voltage gain here, but I am sure you can tell me what is the voltage gain without doing all those. The voltage gain is minus Gm multiplied by whatever is the equivalent resistance we have between collector and emitter. Here, the only resistance we have between the collector and emitter is R naught. So obviously the gain is going to be minus Gm multiplied by R naught. Let us directly write it. AV is minus Gm R naught. Now we know Gm or the transconductance is IC by Vt and R naught is Va by IC. Then the gain will be minus of IC by Vt multiplied by Va, the early voltage divided by IC. IC and IC can be cancelled. We get Va divided by Vt. Va is the early voltage, Vt is the thermal voltage. Both Va and Vt are the intrinsic properties of the transistor and the gain only depend on them. So we can call minus Gm R naught the intrinsic gain of the transistor. Let us write this down. Let's go to the next case. Here I am going to include the resistance of the input. I have the input over here. I am connecting a resistance Rs in series to it. I have taken S for source. It is the resistance of the input source. How will this change our small signal model? Well, it will look like this. Rs is connected between the base and the positive terminal of the input. So I have connected it between the base and the positive terminal of the input in the small signal model also. Let us see how it will change the voltage gain. The first and most important change is this. V input is no more directly connected between R pi. So V pi is not going to be equal to V input. See this. We have ground here. It goes to V input, then goes to Rs, goes to R pi, which again goes to ground. So technically we have a loop here. We can call it the input loop. The input voltage will be divided between Rs and R pi. V pi is going to be V input divided by Rs plus R pi multiplied by R pi using voltage division. Let us write it down. Again, let us apply KCL at the collector. We have two currents. V output by RC is going out of the node. Gm V pi is also going out of the node. According to Kirchhoff's current law, the sum should be equal to 0. We get Gm V pi plus V out by RC is equal to 0. But V pi over here can be written as R pi by Rs plus R pi multiplied by V input. Let us replace it. Let's take V output by RC to the other side. It will become minus V output by RC. Now to get the voltage gain, we have to write an expression for V output by V input. We have V output here, we have V input here. We can easily write what is V output by V input. I'll have to take negative to the other side, RC to the other side, and V input to this side. This is what we get. V output by V input will be negative Gm RC multiplied by R pi by Rs plus R pi. Without the resistance of the source, our gain was minus Gm RC. Now it is minus Gm RC divided by Rs plus R pi multiplied by R pi. This factor is going to decrease our gain. We call it the attenuation factor. Now, let me introduce you to a problem we have. We know the collector current IC is given by Is e raised to VBE by Vt. Here Vt is the thermal voltage, it depends on temperature, which means the collector current will vary with the variation in temperature. Also, it depends on VBE, the base emitter voltage. When we do the biasing, VBE is a constant and we will get a constant collector current. But our input is sinusoidally varying. When we apply the limit, VBE will become sinusoidally varying, which means IC will become sinusoidally varying. Now, transconductance GM is given by IC by VT. So, whenever IC varies, that means GM is also varying. Now, the gain of our amplifier is minus GM/RC, it depends on GM. In fact, it is directly proportional to GM. For example, if there is a 20% change in GM, there will be a 20% change in AV. So, our problem is that our gain is not stable. It is varying because it depends on GM too much. We have to somehow make it less dependent on GM. This is what we do. Include emitter degeneration. This will be case 5 of us finding the voltage gain. I have added a resistor at the emitter and I am calling it RE. If we draw the small signal model, this is how it will look like. There is an extra resistor at the emitter. Once again, across RC, we have a potential V output. So the current through RC will be V output divided by RC according to Ohm's law. Let's do the analysis. In the earlier cases, V input was directly connected across R pi. But right now, you can see that it is not the case. Let us see the input loop. I start from ground, then I go to V input, I go to R pi, I reach emitter, then I have RE, then I go to ground. So V input is not directly connected across R pi, it will be divided between R pi and RE. So V input is going to be potential across R pi plus potential across RE. Let us write it down. By applying Kirchhoff's voltage law in the input loop, you get V input is V pi plus VRE. Now, like we always do, let us apply KCL at the collector node. I can see two currents. There is V output by RC going out of the node and GM V pi also going out of the node. According to Kirchhoff's current law, the sum has to be equal to 0. So GM V pi plus V out by RC should be equal to 0. From this equation, we can write V pi is minus V output divided by GM/RC. Let it be there. Let us apply KCL at the emitter node now. We have a resistor R pi across which the voltage is V pi. So the current that flows through it should be V pi by R pi. Since V pi has positive potential here and negative potential here, this current has to flow in this direction. Let's mark it in here. Also, current through RE will be the emitter current IE. Let us now apply KCL at the emitter node. I can see three currents. One is the GM V pi that is coming into the node. Another one is the V pi by R pi that is also coming into the node. Then there is IE that is going out of the node. So I can write GM V pi plus V pi by R pi will be equal to IE. I want to write an expression for the potential drop across RE. Current flowing through RE is IE, so potential drop will be IERE. But IE is this much. So I can write VRE is GM V pi plus V pi by R pi multiplied by RE. In this equation, we have V pi here and here. But we already found V pi is minus V out by GM/RC. Let us replace both these V pi's with minus V out by GM/RC. Then this is what we get. Minus V out by RC minus V out by GM/RC R pi, the whole multiplied by RE. Or we can write minus V out RE by RC minus V out RE by GM/RC R pi. We got V input is V pi plus VRE. But V pi is minus V out by GMRC and VRE is minus V out RE by RC minus V out RE by GMRC R pi. So we can write V input as minus V out by GMRC, which is V pi. This whole thing is VRE. Over here in the denominator, we have GMRC R pi. We know R pi is beta by GM, which means GM R pi is equal to beta. Here we have GM R pi. Let us replace it with beta. Now we have to add all of these three fractions. Obviously, they have different denominators, so let us try to make a common denominator for all of them. I will multiply and divide the first term with beta. That gives me minus beta V out divided by beta GM RC. For the second term, I only have RC in the denominator. To make it beta GM RC, I will multiply it and divide it with beta GM. That gives me minus beta GM REV out divided by beta GM RC. For the third term in the denominator, I only have beta RC. To make it beta GM RC, I have to multiply and divide this term with GM. It will become minus GMREV out divided by beta GMRC. Now that all the three fractions have the same denominator, we can write the whole sum like this. Negative of beta V out plus beta GMREV out plus GMREV out divided by beta GMRC. We have V out in all these terms. Let us take it out as common. Here we have beta GMRE plus GMRE. We can write it as GMRE multiplied by beta plus 1. Now what we have to find out is the voltage gain, which is V output divided by V input. We have V input on the left hand side and V output on the right hand side. We can easily write an expression for V output by V input. It is negative of beta GMRC divided by beta plus 1 GMRE. Let us divide the numerator and the denominator by beta GM. Then the numerator will simply become RC. In the denominator, we have beta. If you divide beta with beta GM, you will get 1 by GM. Here we have beta plus 1 GMRE. If you divide it with beta GM, GM and GM gets cancelled and you get beta plus 1 by beta RE. Now we know beta is supposed to be a large value. As an average, if you take 125, beta plus 1 by beta will be 126 divided by 125, which is approximately equal to 1. So we can take beta plus 1 by beta to be approximately equal to 1. Then the gain will become negative of RC divided by 1 by GM plus RE. We did the whole thing to make our circuit less sensitive to the variations in the transconductance GM. Because earlier, without emitter degeneration, our gain was minus GMRC. Gain was directly proportional to GM, and a 20% change in GM would cause a 20% change in our gain. Right now, our gain is minus RC divided by 1 by GM plus RE. Obviously, the change in the transconductance does not affect the gain very much. Also, while designing, if you make sure that RE is very much greater than the value of 1 by GM, in the denominator, 1 by GM plus RE can be approximated to just RE, and the equation for the gain will become minus RC by RE, completely independent of GM. Gain only depends on the resistors at the emitter and collector. But we know resistance also depends on temperature. Will that be a problem? Well, actually, no. Because here we have resistances in both the numerator and the denominator. So whatever happens to RE will also happen to RC and they will cancel each other. So we get a very stable gain because even the resistance errors cancel themselves. Let's take an example and give some values. IC is 1 milliampere, RC is 1 kilo ohm, RE is 100 ohm. IC is 1 milliampere, RC is 1 kilo ohm, RE is 100 ohm. Gm is IC by Vt, so it will be 1 milliampere divided by 26 millivolt, or we can write 1 by 26 ohm. Now, without degeneration, our gain is minus GM/RC. GM is 1 by 26 ohm, RC is 1 kilo ohm. So we get gain is approximately negative 38. With degeneration, the gain is minus RC divided by 1 by GM plus RE. We have all the values. If you give the values, you get around minus 7.9. Now, this is a problem. Earlier, we had a gain of minus 38, but it was unstable. Now, the gain is stable, but it has become significantly lesser. It is almost 5 times lesser than our previous gain. So, we have to do something to increase the gain without losing the stability. This is what we do. We will add a capacitor parallel to RE. Since it is connected at the emitter, I will call it CE. Now, how does this help? We know capacitor only lets AC signals pass through it. It will block all the DC signals. When we do the biasing, that is when the input is not applied, there are only DC signals in the circuit and the capacitor will act as an open circuit, which means it is as if the capacitor is not there at all. But when the AC signal input is applied, the capacitor will act as a short circuit only for the AC input signal. So technically, it is as if the capacitor is only there for the small signal input. While doing the biasing, it is as if it is not there. Let me show you what changes in the small signal model. For that, I will take our original small signal model with emitter degeneration. We have RE over here. Now, small signal model is only for the small signal input. Since the capacitor affects the small signal model since it is AC, we have to include it in the small signal model. It is connected across RE parallel to it. So we have to connect it in the small signal model over here, parallel to RE. Again, we said capacitors block all the DC signals and let all the AC signals pass through it, which basically means it will act as an open circuit for DC signals and closed circuits for AC signals. In the small signal model, we only have AC signals, which means the capacitor will act as a short circuit. Now, what happened is RE has been shorted, which means the emitter current that comes from the emitter node obviously will go through the short circuit instead of RE because that is the easier path. So, even if you remove RE, nothing changes in the circuit. Let's remove it. The emitter simply gets grounded. Let's show it in a better way. So, in the small signal model, it is as if RE is not there at all, which will make the gain minus GM/RC instead of minus RC divided by 1 by GM plus RE. It is as if the capacitor is there in the circuit for the DC analysis, that is when we are doing the biasing, and it is not there for the small signal model. Let us write this down. The capacitor acts as a short circuit for the AC input signal and as an open circuit for the DC biasing. In the small signal model, our signal is AC, so it gets shorted. By shorting the capacitor, the resistor also gets shorted, so it decreases RE only for the AC signal and thereby increases the gain. The gain will now go back into minus GM/RC. So this is what I have to ask. Without emitter degeneration, our gain was minus GM/RC. Then I told you it is too much dependent on GM, so we introduced RE. But then I said the gain is too low and introduced CE that bypasses RE in the small signal model. That made our gain back into minus GM/RC. The gain is once again directly proportional to GM. Did I just run in circles? Well, I did not. Remember, in the last video, we learned about biasing the circuit with emitter degeneration. What did adding RE do to our circuit? It made sure our Q point became stable. That means IC became stable. If IC is stable, then GM is stable because GM is IC by VT. If GM is stable, then our gain is also stable. See what I did there? In the small signal model, the capacitor will be there and therefore RE will not be there. If RE is not there in the small signal model, it cannot decrease the gain. So the gain is high plus it is stable. Since the capacitor bypasses the resistor Re to prevent it from reducing the gain, it is called the bypass capacitor. Now, there are two more places where we can add capacitors. One is at the base, I will call it CB. One is at the collector, I will call it CC. We call them the coupling capacitors. CB is at the input, so we can call it the input coupling capacitor. CC is at the output, we can call it the output coupling capacitor. The input and output coupling capacitors connect different stages of a circuit without affecting the biasing. Let me show you how. See, in the circuit, I have applied the voltage divider bias. I would have carefully calculated all the values of R1, RC, RE, R2, CE, everything so that my circuit is biased properly. Now, I am applying V input at the base. V input is probably coming from another circuit. We always consider V input to be sinusoidally vary. What if it has a DC value? Remember when we did this? We found out that the output of the common emitter amplifier is an inverted and amplified version of the original input signal with a DC value of 1.5 volt. So it is possible that our input is also coming with some DC value. Obviously, I do not want the DC value to affect the biasing of my circuit. I have carefully designed everything so that my biasing values are fixed. I only want the AC signal to be applied at the base. Nothing DC should come in. What do? We put a capacitor there. So even if V input has a DC value and some AC signal, only the AC signal will go to my base. We do the same thing at the output also. We saw the output can have an AC signal plus some DC value. Obviously, I do not want my DC value to affect the next stage of the circuit. Most probably, I am taking the output and giving it as an input to some other circuit. I do not want the DC value in my output to affect the performance of that circuit. So to make sure, even if my actual output has a DC value and an AC signal, only the AC signal goes out, I add a capacitor over here. Amplifiers with coupling capacitors are called RC coupled amplifiers. Now, the question is, how do they change our small signal model? To understand that, I have taken the small signal model of our circuit with CB, CE, and CC. Since we have used voltage bias in the example, we have R1 and R2. In the small signal model, you can see R1 here and R2 here. I have shown CB at the base, CC at the collector, and CE at the emitter. Previously, I told you CE gets shorted in the small signal model because the signal is AC. Actually, there is something else I should add to that. We know capacitive reactance XC is given by 1 by omega C. It depends on omega, the frequency of the signal. If the frequency is very low, capacitive reactance will be high. If the frequency is higher, capacitive reactance will be smaller. So we can say that for low frequency signals, XC is high. For mid-frequency signals, that is higher than low frequencies, XC is low enough to be ignored. So in our small signal model, we can ignore these capacitors only if the frequencies of our signals are on the higher side. If they are too low, then the impedance will be high enough that we cannot ignore them. Since in this video, we are only discussing the low and mid-frequency input signals, let us conclude this way. For low frequency input signals, we have to consider the capacitors, and for mid frequency input signals, we do not have to consider them. You can see that in the low frequency case, I have included all the capacitors, and in the mid frequency case, I have shorted all the capacitors. And when I shorted CE, RE became shorted, so I removed it. So we can say that as the frequency of the input signal decreases, the capacitive reactance increases and their effect in the small signal model also increases. Since CE is not shorted, RE will not be shorted. We already know how the presence of RE in the small signal model decreases the gain. So as frequency decreases, effect of CE increases and effect of RE increases in the circuit. As the effect of RE increases, we know how the gain decreases. Even the coupling capacitors CB and CC will contribute in the decrease of the gain. But for higher frequencies, all the coupling capacitors and the bypass capacitor is shorted, so the gain will remain the same. So for low frequency signals, gain decreases with decrease in frequency. And for mid frequency signals, it remains the same. With this idea, let us plot the frequency response of an RC coupled common emitter amplifier. By frequency response, we mean how the gain changes with the frequency of the input signal. For that, I have taken a graph with gain on the y-axis and frequency of the input signal on the x-axis. First, let us divide the frequency into three. Assume this much is considered low frequency, this much is considered mid frequency, and whatever frequencies are greater than this is considered high. We already saw that the junction capacitances are ignored for both low and mid frequencies, so we do not have to worry about them changing our gain. We also saw that the gain decreases for low frequencies due to the coupling and bypass capacitors, so we can show it in the graph like this. Gain decreases with decrease in frequency. For mid frequency signals, even the coupling and bypass capacitors can be shorted, so the gain remains constant. Gain is constant. Now, what happens if the input signal has higher frequencies? We'll find that out in the next video. Let's go to case 5 of calculating the voltage gain of a common emitter amplifier. Cascaded stage, which basically means I will take the output of a common emitter amplifier and give it as an input to another common emitter amplifier. This is the first stage and this is the second stage. Output of the first stage is taken from its collector and it is given to the base of the second stage. Final output is taken from the collector of the second transistor. I have called the output of the first stage as Vx. Let us see how the small signal model will look like. This is the small signal model of the first stage. I have given the input at its base. There is R pi 1, there is GM1 V pi 1, there is RC1, and the output is Vx. I am going to apply this as an input to the small signal model of the second stage, like this. V pi is applied to the base of the second transistor. There is R pi 2, there is GM2 V pi 2, there is RC2, and the final output taken at the collector of the second transistor. Now, what will be the gain of the first stage? That is Vx divided by V input. If you take a look at this much, you can see it is a normal common emitter amplifier and its gain is minus Gm times whatever is the equivalent resistance we have between the collector and emitter. Here the question is, what is the equivalent resistance we have between the collector and emitter? This is the collector of that transistor. This is its emitter, which is basically the ground. Between the collector and the emitter, we have RC1 and we have R pi 2. They are in parallel. So the gain of the first stage is not going to be just minus GM RC, it is going to be minus GM RC parallel to R pi 2. Let us write it down. Now take a look at the second stage. We have this much. This is also the small signal model of a normal common emitter amplifier. So the gain is going to be minus Gm times whatever is the equivalent resistance it has between the collector and emitter. Here is its collector, here is the emitter. The only resistance I can see is RC2. So here the gain is going to be minus Gm RC2. So gain of the first stage AV1 is minus GM1 RC1 parallel to R pi 2 and gain of the second stage AV2 is minus GM2 RC2. Gain of the first stage is its output divided by its input. Its output is Vx, input is V input. So AV1 is actually Vx by Vin. For the second stage, output is V out, input is Vx. So its gain is V output divided by Vx. The ultimate gain of the cascaded stage will be the final output divided by the original input, V out divided by V input. To get that, we simply have to multiply these two. If we multiply Vx by Vin with V out by Vx, Vx and Vx will get cancelled and we will get V output by V input, which is the final gain. Here Vx by Vin is AV1 and V out by Vx is AV2. So we can say the final gain is the product of the individual gains of the two stages. So V out by Vin will be GM1 RC1 parallel to R pi 2 multiplied by GM2 RC2. Now assume that we are including the early effect. How will the gain change? If we include the early effect, for both transistors, we'll have to add R naught between their collector and emitter. So for the first stage, we'll have a resistor over here. Let's call it R naught 1. So when we calculate the equivalent resistance between the collector and emitter, we'll have RC1 parallel to R pi 2 parallel to R naught 1. Similarly, for the second transistor, we'll have R naught between the collector and emitter. Let's call it R naught 2. So here, when we calculate the equivalent resistance between the collector and emitter, we'll have RC2 parallel to R naught 2. The expression for gain will be like this then. We will get an extra R naught 1 over here and an extra R naught 2 over here. This was the last case for calculating voltage gain. Let us move on to input impedance. For case 1, I have taken a simple common emitter amplifier. First, let us take the small signal model. Input is to be given at the base and I want to find out the input impedance. We have learned how to find input impedance in two cases. When there are no dependent sources and when there are dependent sources. Here obviously we have a dependent source. GMV pi is dependent on the voltage over here. So to find the input impedance, we have to shut down all the independent sources and connect a voltage Vx over here. Calculate its relationship with the current that will flow in this direction, Ix. Once we get the relationship between Vx and Ix, we can take Vx divided by Ix that will give us the input impedance. Here, if you look at the input loop, I'll start from ground. I have Vx, I go to R pi, then I go to emitter, again back to ground. So technically Vx is directly connected across R pi, which means V pi is equal to Vx. Ix is the current that will be flowing through R pi, but current flowing through R pi is V pi by R pi. So we can write V pi is Ix R pi and it is also equal to Vx. So Vx is Ix R pi, which means Vx by Ix is R pi, which means our input impedance is simply R pi. Let's take the second case where we will include the resistance of the input. I have an Rs for resistance of the source. In that case, the small signal model will look like this. V input is connected at the base, but it is an independent source, so we have to remove it. I will short it. Again, we have to find the input impedance, which means we have to apply a source Vx at the input, which is the base. Ix will be whatever current that flows in this direction over here. We have to find a relationship between Vx and Ix. Once we do that, we can take Vx by Ix, which will give us our input impedance. Again, let us take the input loop. I'll start from ground, go to Vx, there is Rs over here, and there is R pi over here, and then I go back to ground. Basically, we are applying a potential Vx across Rs and R pi who are in series. So Ix will be Vx divided by Rs plus R pi. That means Vx by Ix will be R pi plus Rs. So our input impedance is R pi plus Rs. Let's take the third case. Include emitter degeneration. I have added Re at the emitter. In that case, the small signal model will look like this. I have a resistor Re at the emitter. To find the input impedance, I have removed the input and instead I have added Vx at base. Ix is whatever current that flows through here, and we have to find a relation between Vx and Ix. For that, again, I will take the input loop. I'll start from the ground. I go to Vx, then I reach R pi. I reach the emitter. I have the emitter resistance, and I go back to the ground. So Vx is divided between R pi and Re. So we can write Vx is V pi plus Vre. Now, what is V pi? V pi is the potential across the resistance R pi and the current flowing through it is Ix. So V pi will be Ix R pi. What will be Vre? For that, we need to know what is the current flowing through Re. Current flowing through Re will be a sum of Ix and GMV pi. So VRE will be Ix plus GMV pi multiplied by Re. Here again we have V pi and we found V pi is IXR pi. So let us replace it with IXR pi. That gives us IXR pi plus Ix plus GM IXR pi multiplied by Re. Let's open the bracket here. So we get this. Over here we have GM IXR pi Re. What is GM multiplied by R pi? It is beta. So let us replace it by beta. Now we have IXR pi plus IXRE plus beta IXRE. In both these terms, we have IXRE. So we can write it as IXRE multiplied by 1 plus beta. Again, here we have Ix, here also we have Ix. Let us take Ix out in common. That gives us Ix multiplied by R pi plus beta plus 1 Re. What we have to find out is Vx by Ix. Because Vx by Ix is our input impedance. From the equation over here, we can write Vx by Ix. It is R pi plus beta plus 1 Re. Let's put this in a box. We know beta is supposed to be a large value. So beta plus 1 will be approximately equal to beta itself. So we can say input impedance is approximately R pi plus beta Re. So without emitter degeneration, our input impedance was simply R pi. Now it is R pi plus beta Re. We can see that the degeneration increases the input impedance. Is it a good thing or a bad thing? It is a good thing. Remember, we wanted our input impedance to be as high as possible. The larger, the better. Let us now move on to output impedance. In the first case, I'm going to ignore the early effect. So early voltage is infinite. I have a normal common emitter amplifier. Its small signal model will look like this. Input is given at the base, output is taken at the collector. We have to find the output impedance. The first thing to do is remove all the independent sources. We only have one independent source here, that is the input voltage. So I'll have to short it. So the base gets shorted. The next thing we have to do is, since we are finding the output impedance, I'll have to add a potential Vx over here and calculate its relationship with Ix, which is the current that will flow in this direction over here. Now, take a look at R pi. Its one end through the base goes to the ground. The other end through the emitter again goes to the ground. Basically, it is shorted. Potential across R pi is 0, which means V pi is 0, which means GMV pi is 0. GMV pi is the current that flows in this branch. Since GMV pi is 0, no current is flowing through that. That means Ix coming from here is entirely going through RC. RC is directly connected across Vx. So the potential across RC is Vx, current flowing through it is Ix. So we can easily say Vx is Ix RC. Let us write all of this down. Since base is grounded, we found V pi is 0, which made GMV pi 0. Since no current has to flow in this direction, all of Ix is flowing through RC. So we get Vx is Ix RC. That means Vx by Ix is RC. Vx by Ix is our output impedance. So the output impedance is RC. Let's take the second case where we have to include the early effect. Early voltage is a finite value. In that case, the small signal model will be like this. Since early effect is included, we have R naught between the collector and the emitter. Input is given at the base, output is taken at the collector. The first thing we have to do is remove all the independent sources. The only independent source we have is the input voltage V in. We have to short it. Now, here we have RC and RO, they are in parallel. Let us model them as one resistor whose value is RC parallel to R0. Now, to find output impedance, we have to connect Vx at the output node and calculate its relationship between Ix, which will be the current flowing here in this direction. Here again, you can see that R pi is shorted. That means potential across R pi is 0. V pi is 0. If V pi is 0, then GM pi is 0, which means no current is flowing in this branch, which means all of Ix will be flowing through RC parallel to R0. RC parallel to R0 is directly connected across Vx. So the potential across it is Vx. So we can easily say Vx is Ix multiplied by RC parallel to R0. Let us write this down. Since R pi is shorted, potential across it V pi will be 0. If V pi is 0, GM V pi is 0. Then we get Vx is Ix multiplied by RC parallel to R0. From here we can write Vx by Ix. It is RC parallel to R0. So the output impedance is RC parallel to R0 if we consider the early effect. Let us see the third case. Here we have to include emitter degeneration and early voltage is infinite, which means we can ignore the early effect. I have added RE at the emitter. The small signal model will look like this. First thing I have to do is remove V input. Then the base will get shorted. Now I have to add Vx at the output and find out its relationship with Ix. Now the analysis of this is not going to be as simple as the previous ones because R pi is not exactly shorted. One end of R pi goes to the ground, true, but the other end is actually going to Re. Through Re, we reach the ground. We could say that R pi and Re are basically in parallel. See there, these two ends are connected. The other two ends are also connected to the ground. See there, these two ends are connected. So whatever is the potential across R pi, it is going to be exactly the potential across Re since they are in parallel. Negative potential of R pi is here. Since it is connected to this end, Re will get negative here. Positive potential of R pi is here. Since this gets connected to this end of Re, it will get positive potential here. Basically, Re will have V pi across it. Positive potential here, negative potential here. Let's write this down. R pi is parallel to Re, so Vre is equal to minus V pi. Why minus? Because we got negative here and positive here. Now let us apply Kirchhoff's current law at the emitter. I can see three currents. R pi has a potential V pi across it, so there will be a current V pi by R pi. GM V pi will be coming like this. Across the emitter, we have a potential drop of V pi, negative here, positive here. So we can consider the current through Re to be V pi by Re in this direction, from positive to negative, or minus V pi by Re in this direction. According to Kirchhoff's current law, the sum of these three currents should be equal to 0. So we can write V pi by R pi plus GM V pi plus V pi by Re is equal to 0. You can see V pi is common in all these three terms. Let us take it out as common. V pi multiplied by 1 by R pi plus GM plus 1 by Re is equal to 0. Do you think there is any way this sum will become equal to 0? No, right? 1 by R pi is a positive value. GM is positive, 1 by Re is positive. There is no way this is 0. So if the product has to be 0, that means V pi has to be 0. Well, we had to do some work, but finally we see that V pi is still 0. If V pi is 0, then GM V pi is 0. No current will flow in this branch. That means all of Ix will be flowing through RC. RC has a potential Vx across it. So Vx is going to be Ix RC. Vx by Ix is going to be RC again. That means our output impedance is again just RC. Let's see the final case. Here we have to include the emitter degeneration. Early effect has to be included because early voltage is finite. We also have to replace RC by a current source. In the circuit diagram, I have RE here. I also have replaced RC with the current source IC. Now, the small signal model will look like this. To remove the current source, I have opened the circuit over here. To include early effect, I have added R0 between the collector and emitter. Input is given at the base, output will be taken at the collector. To find the output impedance, first thing we have to do is remove the independent source V input. Base will become grounded. By doing so, just like we saw in the earlier case, R pi and RE will now become parallel to each other, which means potential across RE will be V pi with negative potential here, positive here. Now to find out output impedance, we have to connect Vx at the collector where we'll be taking the output from and find its relationship with Ix, which is the current flowing here. Let's make the circuit a little bit more simple. R pi is in parallel with Re. So let us replace this whole thing with just one resistor whose resistance is R pi parallel to Re. Now IE flows like this. At this junction, GMV pi will flow in this direction and the rest will flow through R0. But these two currents again recombine over here. So the current flowing here is going to be Ix again. That means the current flowing through R pi parallel to Re is Ix. Ix flows in this direction. So the potential drop across R pi parallel Re should be positive here and negative here. But we have taken V pi with negative here and positive here. So V pi will be negative of Ix multiplied by R pi parallel to Re. Now if V pi is this much, then Gm V pi will be Gm multiplied by this. So the current that is flowing in this branch is minus Gm Ix multiplied by R pi parallel to Re. Now what will be the current that flows through R0? We can easily find that by applying KCL at this point. Ix is coming in, out of which minus Gm Ix R pi parallel to Re is flowing in this direction. The rest will flow in this direction. So the current through R0 will be Ix minus Gm Ix R pi parallel to Re. Minus minus will become plus. So the current in this branch will be Ix plus Gm Ix multiplied by R pi parallel to Re. Now that we have our simplified circuit, let us apply KVL in the output loop. I start from the ground, there is Vx, then I go through R0, I reach the emitter, I go to R pi parallel to Re and then I go back to ground. So first I have Vx from negative to positive. As I go on, I can see R0. There will be a potential drop across R0. Current flowing through R0 is Ix plus Gm Ix R pi parallel to Re. So the potential drop will be R0 multiplied by that. Since current is flowing in this direction, R0 should have positive potential here, negative potential here, which is opposite compared with Vx. So I have to write minus R0 multiplied by Ix plus Gm R pi parallel to Re Ix. As I further go on, I reach R pi parallel to Re. There is a potential drop there. Current flowing through R pi parallel to Re is Ix. And it is flowing in this direction. So it should have positive potential here, negative potential here. Again, in the opposite direction of Vx, so I will write minus Ix multiplied by R pi parallel to Re. According to Kirchhoff's voltage law, this sum should be equal to 0. From this equation, we can write Vx is Ix multiplied by R naught plus Gm R naught multiplied by R pi parallel to Re minus R pi parallel to Re. Let's keep Vx on one side of the equation and take all the other terms to the other side. We get this. You can see that in all these terms we have Ix. So we can take Ix in common on the right hand side. We get Ix multiplied by R naught plus Gm R naught R pi parallel to Re plus R pi parallel to Re. In both these terms, we have R pi parallel to Re. Let us take it in common. We get Ix multiplied by R naught plus R pi parallel to Re multiplied by Gm R naught plus 1. What we want is Vx by Ix, which is our output impedance. From here, we can easily write Vx by Ix. Vx by Ix is R naught plus R pi parallel to Re multiplied by Gm R naught plus 1. So the output impedance is R naught plus R pi parallel to Re multiplied by Gm R naught plus 1. So that's all about it for today. I hope I have given you enough tools to determine the voltage gain, input impedance and output impedance no matter how the common emitter amplifier circuit is configured. See you in the next video and don't forget to subscribe.